And actually, let me do this now so I don't forget. This is a great thing to record. Here's the practice test. Glance at it and then put it in there. So last time we got through 2.6. 2.6 was basically, for the most part, was a review of horizontal asymptotes from pre-calculus. But then we expanded on the idea to go beyond just rational functions. We could have some radical stuff in there, some other freaky stuff. Okay, so basically it was just limits at infinity, some kind of infinite limits, letting x get really big or positive, really big negative, either way. So I think we pretty much finished section 2.6. We have 2 sections left. We should be able to knock them out. We actually got a little bit into 2.8, believe it or not. I didn't say it at the time, but I didn't want to freak anybody out. Let's do some specific to 2.7. So let me remind you about what we did last time. If we have a function... So find f prime using the limit definition of derivative. So I totally understand that some of you guys know derivatives. This is so easy. It's like one step. I don't give a shit. So derivatives are so easy because there's a lot packed into them that you must understand. Even if you don't think you need to, I'm here to help you do it because you have to. There are shortcuts we're going to learn very, very soon. Beginning of chapter 3, we're going to learn some major shortcuts to derivative. We're not going to do a bunch of limit stuff. And I know you hate them. You hate them because they're hard, and they're hard because of the concept. They're the reason the derivatives work. What the hell does this mean? Anybody remember the limit definition of derivative? Yes?
It's the limit of the difference quotient.
Actually, what's the difference quotient?
F of x plus h minus f of x all divided by h.
And where's that come from?
Slope.
Wait.
Sorry.
Yeah, well, f of x plus h minus f of x. F of x is taking the place of y. So where's that f of x plus h minus f of x over h? Where's that coming from? It comes from the algebraic definition of slope, y2 minus y1. So I really desperately want you to realize this is just the next natural step from algebra. Well, we got slopes of straight lines. That's amazing. I want to get slopes of things that aren't straight, which means that the answer to a slope of a curve has got to be its own function. We're creating another function through this process. So that's what we're going to do right now. I'm going to create this function that happens to describe the slope of this everywhere, but it's its own function in its own right. In fact, this function itself describes the slope of some other function. I can kind of go backwards. That would be the next thing we learn in calculus, is how to anti-differentiate. Take the antiderivative of something. Because in math, what do you always have to be able to do? You have to be able to go both ways. Right? Okay. So, this is the idea. When I say using limit definition derivative, this is what I mean. Okay, try to do that. See how far you can get. Even if you weren't here last time, just start analyzing this. There's your f of x. Just got to figure out what f of x plus h is and throw that stuff in there. Just to give you guys a little help, be really careful about throw that in. It's going to be minus the whole damn thing. I like the idea of building what I'm working with. I'm going to build this. I'm going to build this piece. Build. Chunk it in there. Right? It's construction work. I love it. Really collar construction, but still constructing something. So you see a lot of stuff happening up there, right? In fact, anytime you have a polynomial, for damn sure, everything that didn't have an h on the top should die. Because again, what's the problem? Why do I get 0 over 0? Because the top and the bottom both have a factor of h. So if you don't have something cancel on top, you've done something wrong. Because polynomials are very, very simple. If one works a certain way, they all basically work that same way. Some way conceptually, they all work that same way. So here I get the x squares cancel, the 2x, the 2x's cancel, right? Minus the negatives plus. And so I'm left with 2xh plus h squared 2h all over h. And then what happens? Yeah, take the h. So it's killing h and everything. Die, 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 die. Notice something remarkably important. I know it seems like it isn't. Every step I've written, I have the limit there. I never want to see something like x squared plus 2xh equals x. I mean, you have the limit there for some of the steps you take to make sense. Do not forget this, dude. It's what's letting you do certain things. So now the limit as h goes to 0. Yeah. And what do I get here?
2x minus 2.
Yeah, 2x minus 2. Now some of you guys know, doesn't it look like that 2 just came down here? And in fact, what's the slope of negative 2x? Negative 2. So that piece is linear. That slope is easy. I can just look at it and know the slope is negative 2. This is the one that's a little bit freakier. But yeah, any power, we're going to learn that the power comes down and it goes down by 1. That's going to be our first derivative. We don't know it yet. Don't get too excited. I see some of you guys like, oh, shit. What is that function we just calculated? What does it do? What is it? I haven't actually identified it correctly yet. What is that? What is it? What is it? So what do I put there? F prime. That little prime means the first derivative. I could have two primes, which means the second derivative. So forth. No obvious problem. So let me ask you this. This is a question that you're going to see a lot. This type of question right here. Find the equation of the tangent line to f of x at x equal to, let's say, 3. Do you guys remember from algebra? Find the equation of the line that does shit. What did you need to figure out to find the equation of a line? Point and the slope. Right? Because then I can do, if I wanted to, I could do this funky one. Y minus y1 equals m, then x minus x1. Or hopefully everybody knows how to use this and figure out what b is, if you don't know what the y-intercept is. So, in this case, how do I find the point? What's the point that I know my line goes through? Yeah, what's the only thing I know about where I am on this function? X is 3. So what's the point there then? What's the point that my line is going to go through? Three. I love it. So 9 minus 6 is 3. Yeah, so there's the point. Now how do I find the slope? Plug it in where? Yeah, slope. So we got the point. Point is the same as always. Just plug x in, see where the hell it is. This should feel a little bit like algebra, except now we're using derivatives to answer the m question. Before it would be like, it's perpendicular to this other line. And you're like, all right, let's find that stupid thing and turn. Right? You had algebraic ways to find the slope. Now we have a calculus way to find the slope. Same problem. It's just got a different way to find the slope. So how to get the slope? F prime of 3. 4. I love it. What does that mean exactly? What's that 4 mean exactly?
The slope at 3.
Yeah, the slope of the tangent line at 3 is 4. I love it. So right there, right at 3, this thing that has a positive slope, if it came off the tracks, like it's a roller coaster or something, or if I was spinning something on my hand and let it would go off with that slope. That's what the tangent line is. If it's being stuck to this track because of magnetism or something and suddenly the whole thing goes off, it's going to be, that's the way it starts to go immediately. Right after that, it's got a slope of 4. Which gravity's going to suck it down, you're just going to die. Oh, okay. So now I can do either one of these. Whatever you feel like. So if you do this first one, it would be y minus 3 equals m times x minus 3. Does that feel familiar at all? This is going to happen a lot. This. As we learn new derivative rules, there's always going to be a problem like this in the homework, and there's always going to be a problem like this on my tests. Because this is the fundamental thing that derivatives do for us. So I get y equals 4x minus 12 plus 3. I want to show you the visual of this. Just to show you. Do you guys know about Desmos.com? Sorry, kicks ass. If we had a computer lab for every math class, we do a lot more stuff in Excel and Desmos and stuff. We know, so we use GraphCalculator. I'm going to show you on Desmos. This is just so beautiful.
multiplication.
So this, anybody know what this looks like? This is this is a beautiful place for me to remember to say this. My God, when you have to graph something, do you guys remember what I called pre-calculus? I tell my pre-calculus students this, not to be scary, but just to get them to understand the reality. Pre-calculus is graphing hell. So here, I better see some detail in these damn graphs. I love the questions. Graph this using shifts. Okay. Good. No scale. Even with the scale, give me some freaking work. Right? Yes.
Would you have us use graph paper to do the homework?
Totally up to you. Some of you guys, if I was in this class, I would tell me, use some graph paper, Jeff. You draw horrible. And I would say, I know, I'm sorry. Do it. If you're cool with not, and you're decently careful, you can do it that way. You can do all the homework on graph paper. That's what I used to do. Knowing myself, I needed extra help to keep straight. I'm like all over the damn place. Oh man, and I really love, graph this cosine shifted, and I get this. And that's it. That's all I get. No. Number one, if you did it by hand, where's that work? Number two, if you did it in the calculator, at least copy some more detail down. Shit. Number three, if you do that, I'm still going to ding you, but at least it looks better. This is shit. Okay. You should know better. All right. What was I going to say? So this guy, real quick, before you go up there, what should this look like? Anybody can tell me anything about this?
Looks like a parabola.
Parabola. I love it. Opening upwards. What's another good thing to tell me? Some more detail about it. Okay, the vertex you can figure out. Something even better than doing that first is actually what's the x-intercepts. How do you factor this? How do you factor this? Out comes x. What's left? So what's the intercepts? X-intercepts. 0 and 2. So where's the vertex got to be?
1.
At 1. When you plug a 1 in, what do you get? 1 minus 2. All right, look, that's quick. That's work, quick, scale, decent sketch. Doesn't have to be perfect, but it's got to have some work and some scale at least, a little bit of detail. Not this, No. All right, so here. Now at 3, the output was 3. Let me see if I get lucky. Yeah, sweet. Make that big. Cool. So we're trying to find the tangent. So it makes sense that we got a positive answer. It also makes sense that it's decently large, right? Here, what is it right here? What's the slope? 0. And then it gets bigger, positive, bigger, positive. Back here, of course, it's negative. I like it. Gets bigger, positive. So here should be decently large positive. So 4 makes sense at least. I can't look at that and know it's 4, but I can look at it and say 4 makes sense. So on top of this, here's the tangent line then, touching that parabola. So that's what I should see if I plot this and this in the calculator or on Desmos. I should see that picture basically. Maybe not those colors. Nothing. It's not. I love to play around with this shit. Maybe I have to do it here. Oh, there it is. So the reason I've got to go to Desmos right now is because they don't have my TI emulator on this computer. No idea. So if you've never used Desmond, I mean, it's just really nice. You can download an app for your phone. I have no stake in the company, so I'm not trying to sell you anything. But it's a beautiful two-dimensional graphing app. What was it? X squared minus 2x. So there's that. Hey, look, there's our 3 anchor points. No way. And then I want to graph on top of that 2x minus 2, right? No, not this. Let's do, what was it, 4x minus 9? There we go. Okay, and it's actually the same colors. It's freaking me out. You can't even tell that, I think, but it's green and red. It's awesome. So right here, let's see if I can read it to tell. Right there's 3, right where it hits. Now notice something really interesting. I want to point out a couple things. The tangent line is sort of like the surface of the Earth, really. There's a tangent line that I live on because to me it looks like it's flat. Of course, we all know better. The surface of the Earth is spherical. It's round. So when I zoom in really close to something like we're little ants on the surface of the Earth. We're really zoomed into that function, that circular function of the Earth. It looks straight to me. So as long as you have a smooth function where the slope doesn't change instantly from something to something else, then you're gonna, when you zoom in, it should flatten out and become linear. So that tangent line, we're going to look at it differently later in this course. We're going to call that tangent line the linear approximation. So when I'm really close to 3, that green line is really close to the outputs of the function. Right? So it is a linear approximation for inputs close to 3. Somebody semi-decent with that? No? You don't like that at all? It's in our future. We're going a little ahead. So when I zoom in, that red line does become, if I take this out, when I zoom in here, doesn't that become a straight line pretty quickly? Especially because this is just a nice function, a really stupid nice function. So I put that back in there. Oh, now it's orange. Cool. A lot of things. So on this orange line, 2.452 is 0.808. This one, 2.45 something, is close to that. So the outputs are close to each other. The closer you are to 3, the closer the outputs are. Because at 3, it actually hits that function. Is that cool? Okay. Now notice, I want to do this right now. We're going to do this a lot more later today, but tell me again, where was the slope 0? Yeah, the slope is 0 here. So I'm going to start drawing the slope in blue. Right? I'm going to draw the slope function. I already know what that function is, but I'm going to just like it up. So that means that what I'm about to do is put points that illustrate the slope at that point. So at this point, I should draw this at 0. Because what's the slope at 1? 0. This is really freaky. Your brain rebels against this, and what happens is you just start following the function. But you got to say, brain, stop that shit. Now look at this. Isn't this up here? This red function is up here, but what is the slope? It's really big. Negative. So when I draw the blue line, it's going to be down here. What's happening as I get closer and closer to 1 is it's getting... It's always negative back here, but it's getting less negative. It's getting smaller negative. It's approaching 0. So I start off big negative, gets less negative, and of course what happens once I'm around the corner here? It's positive. So my blue line better be up here, this side, because the slope is positive, that side. Your brain goes, the function is up here. Why are you doing this? Because this should be big negative. In fact, right at this point, what should the slope be? What was the slope here? So what's the slope there going to be? Negative 4, because the symmetry of this. Beautiful, well, perhaps is almost too nice. But anyway. So that should be negative 1, negative 2, negative 3. Let me see if I can find it. Negative 4. Yeah. Decent? Cool? No? And then, of course, over here, like I said, now it starts to be positive, and it's going to go up through there. I should go through that point, but I won't. And of course, we found out that the slope function was, where'd it come? Sure. It was 2x minus 2. Right? And that's pretty much, I'll make a big point there, that is 2x minus 2. That blue line is 2x minus 2. So yes, there will be problems that give you a function and they say trace the slope function given the function. You do what I just did with the blue line. Like it, I've got a little handout we'll look at later to illustrate that. Okay, so let's kind of build backwards a bit here. That was what we did last time, and then there's a little extra stuff I did. So here is what I kind of skipped in 2.7. I want to do a problem specific to 2.7 and try to get you to realize that 2.8 is actually superior to it. So in section 2.7 they'll say this. Let's find that's the front of this. Cubed. At -1. So what they do in 2.7, I want you to realize this. This is really just so you understand what they're doing in 2.7. We know some better shit. I wish they never did what they do in 2.7, but too bad for me. They make this. What's the subtle difference there? So now I'm not just letting x be anything. I'm letting it specifically be that point that I'm interested in. In this case, anybody know what a might be? Yeah, -1, right? Do you see how 2.8's approach is superior? Because I could find it no matter what x is, and then I could plug a -1 in. Or I could plug a -3 in, or I could plug an 18 in, whatever the hell I want to. Here, if I do this process, it's only going to be the slope at -1, very limited. But just so you see what they want in section 2.7, what's this going to look like? Well, what's f of a plus h? A, of course, is -1. Let's do this. So then this is going to be f of -1 plus h. Let's go to h minus 1 cubed minus -1 cubed. It's a good little time for a side note here. It's going to help us out when we develop our first shortcut rule for derivatives. Somebody ever heard of Pascal's triangle, binomial theorem stuff? Anybody never heard of Pascal's triangle? You're like, did he play in the band? It's my triangle. No. Here's Pascal's triangle. It was really exciting. It was going forever. What the hell's going on with that?
It's changing degrees. The top one is the first degree, the second one is second degree, third one is
Oh, like, okay, I got you. The powers.
Yeah.
I love it. So that's the connection to expanding stuff like this very quickly. So for example, what is x plus 1 squared? It's x squared plus 2x plus 1. 1, 2, 1. 1, 2, 1. So x plus 1 cubed is going to be x cubed plus 3x squared plus 3x plus 1. 1, 3, 3, 1. That kicks so much ass. I want to foil my life away. What are you doing? Foil. So, yes, sir.
Are you allowed to solve using Pascal's triangle on the homework, or do we have to?
Shit, yes. This is something you could have been shown before, something that very easily some of you guys have only seen now for the first time. This, but on a more fundamental level, how do you create this triangle? 1 plus 1 is 2. You got the 1s on the outside, and you just keep going. 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 3 is 6, 1 plus 3 is 4, blah, 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 blah. It's based on something called combinatorics. Combinations. Freaky. If I have 2 things, how many ways is there to choose one of them? If I have 2 people, how many ways can I choose one person? 1, 2. That's what that 2 means. If I have 3 people, how many ways is there to choose one person? 3 ways, and so forth, right? So it's based on something called combinations. How many combinations can I create given a certain number to choose from? So if I wanted to, I could use that for this. Or you could just FOIL it out. Here's how it works. It's really kick-ass. I'm going to show you this one. I'll show you another example with a little more messy stuff inside. So I have h cubed. Which level am I on? 1331. I like it. So 1h cubed. Let me just do some plus negative 1 h squared plus negative 1 squared h plus h, yeah, they're h cubed, plus negative 1 cubed. So it's really kind of cool. All h's, no negative 1s. 1 less h, 1 more, 1 less h, 1 more, 1 less h, 1 more. This is exactly what happens when you FOIL shit out. You get all these lower and lower degrees, and there's combinations of the middle degrees. That's why this is based on combinations. You can actually find Fibonacci sequence in here too, if you know what that is. If you don't worry about it. So here I got h cubed minus h squared plus h minus 1. That's exactly what you get if you FOIL that sucker out. If you never want to use Pascal's triangle for me, I don't care. I sort of don't understand you, but it's all good. It's just a shortcut. So this will be down there. H cubed minus h squared plus h minus 1 plus 1 all over h. Those go away. So like always, the h-less stuff goes away. So then you can kill the problem. 1, die, plus 2. And of course I get 1. Woohoo! What's that mean?
Slope at that number.
The slope at this point of this function is 1. Slope of the tangent line at that point is 1. I love it. And then I can ask you to find the equation like we just did. So pretty cool with that? That's what 2,7 does. If you'd rather put an x here and then just put a negative 1 into that function to get the slope, that is, to me, better. Or you can do this way if you want to. If you've already done it, then you've done it this way. You're fine. Somebody semi with me here? If you're not sure, just do it the way they want you to do it in that section.
So say we use a shortcut. Obviously.
No, wait a minute. Now that's not on the table.
Yeah.
Do you mean like just make that 3x squared?
Yeah.
Knowing
And then-
derivatives, which we don't know.
Yeah.
Okay.
And then we plugged in like hypothetically negative 1. We wouldn't get 1.
Good point. Where did I mess up here? Oh, no. Oh, I forgot my 3's. I'm so stupid.
Yeah.
There, right there. 3, 3, 3, 3. So it should be 3. Thank you. I just forgot my 4 little 3's. My whole point, I forgot. So Pascal's triangle, if you want to look that up, if you use it correctly, it makes it really quick to get stuff, right? Now, again, we could have done this whole thing with an x here, and then plugged a negative 1 in at the end to get the same answer. I like it. Okay. So just to remind you guys about something, this is a point that could have been missed pretty simply. If I have a function that tells me, let's say, the number of hot dogs somebody eats in a certain amount of time. All right, anybody know the name Joe Chestnut? Yeah, some of you guys know. Good Lord, dude. He's like, he was, I don't know if he still is, the world record holder for number of hot dogs eaten in a certain amount of times. Gotta have a goal. If that tells me the number of hot dogs that somebody eats after a certain amount of time, what does this tell me? Yeah, and so a better notation to figure out units is that d by dt notation. I don't know if you guys remember this. I talked about it a little bit quickly, but a better way to write the prime notation is this notation. So this is basically the infinitesimal change in hot dogs per the infinitesimal change in time, but in terms of units, hot dogs per whatever t is. Let's say seconds. T is in seconds. So this will be number of hot dogs per second. And then it can interpret other things. What would h prime? So what would h prime of 5 be?
Number of hot dogs is projected to be in 5 seconds.
No, be careful.
It would be the rate at which he's eating hot dogs at t equals 5 seconds.
Yes. So it's the rate that he's eating hot dogs at 5 seconds. So the number of hot dogs per second at 5 seconds. So think about if you're in a car and you step on the gas. So 2 seconds after that, you're going a certain speed. 3 seconds after that, you're going a certain speed. That's what that means. So S's position, S prime of 3 would be the rate at which you're traveling at 3 seconds. I like it. Okay. So I think there's enough info to throw at you for you to be able to do this sheet. Make sure everybody's awake. There we go. We got an eyeball. As always, if you want to work with somebody else, a few other people you can. If you just trust other people, you can work by yourself. Yeah, you can eat, drink in here. If you make a mess, it's your responsibility to clean it up.